Now we will discuss another algorithm called label propagation. Now, label propagation algorithm is also used for for semi-supervised machine learning algorithms, but here we will use it for overlapping community detection. Okay, so label propagation basically says that you have certain labels and you propagate those labels over the iterations, and then using these methods you detect communities. So what is the label here? Here the labels are different community IDs, right, or whatever colors, right. So you can think of colors as different communities. So you basically spread colors over the iterations and you basically color the nodes, and at the end of the day you will have only a few colors remaining, and those colors basically correspond to different communities. Okay. So label propagation is useful when the graph changes over time, because in most of the algorithms that we have discussed so far, BCLAM or click percolation, you need to actually run it on the entire graph. But label propagation is something which is useful when, say, you have already got a graph and you already got the community structure of the graph, and then some nodes have been added, some edges have been added. You only need to look at that part, and then you run the label propagation method again. So you will get the overall community structure. Okay. So this is a very simple algorithm, but this is worth understanding. So there are two types of label propagation methods. One is called synchronous label propagation, other is called asynchronous label propagation. I will discuss these two things one by one. Okay, so let's start with this asynchronous label propagation method. So this is the graph, and you have labels denoted by different symbols. So here I am not using colors, I am using symbols. So we have this heart symbol, right, this moon-like shape, then plus, right, some stop symbol, circle, and some sort of square. Okay, these are different symbols indicating different communities. So at the beginning, you basically, similar to other algorithms, you also assign nodes into different communities. If you look at it here carefully, each node belongs to a separate community. You have separate labels. Okay, and over the iteration, we will basically propagate these labels, these symbols, and we will try to change the labels of nodes. Okay, and at the end of the day, what would happen is that only a few labels will remain intact, and the corresponding nodes of every label will be will form a community. Okay, so this is asynchronous. Let's see how it basically works. So let's start from node 1. So what is the idea here? We start with a node, and then we look at the neighbors, its immediate neighbors, and their symbols, their labels, and we take the majority of my neighbors' labels, and that label, we take the majority label from my neighbors, and that label will be assigned to me. Okay, let's say you have this node, and this is V. It has labels plus. You have it has 3 neighbors. Say this heart shape, and then this circle and circle, right. So the majority is circle, so it will be now this plus will be replaced by circle. Okay, it's kind of a majority voting. And if there's a tie, we basically break the tie randomly. We take any random label. So let's start from node 1, and node 1 has node 1 actually has 3 neighbors, 6, 5, and 2, and all these 3 labels are different. So I choose one. I choose from this thing independently. I choose any one of these labels, or I basically keep my own labels. So let's assume that I keep my own labels, which is star, which is this heart symbol. Now let us move to node 2. Node 2 has this symbol, this one, and this one. Again, you have tie, right? And let's see, this time you choose a heart symbol. Okay, you see here this moon-like symbol is replaced by heart symbol. Okay, because randomly I chose this heart symbol, therefore this was replaced by heart. Okay. Now I move to 3. Now this 3, node 3, you see that node 3 has this one and this one. Again tie, right? So which one I choose? Let's see, I randomly choose this one. So therefore, this will be replaced by stop symbol. Okay. Let's move to 4. So the 4 has one stop symbol, one circle, right? And let's say I randomly chose this stop symbol. So the symbol of node 4 will remain same. Node 5 we have node 5 has this symbol, this one. So square, heart and heart. So the majority is heart. So this circle will be replaced by heart. Okay. Node 6 has heart and heart. So the majority is heart. So this will be replaced by heart. So this is one iteration. So after one iteration, you see that only 2 symbols persist. One is this heart, other is the stop symbol. Okay. So it basically means that after first iteration, you have 2 communities. This is one community and this is another community. All right. So this is called inner iteration. Now in the outer iteration, we repeat the same thing again. We again start from 1 and then we look at the majority and we replace, right? And we keep on doing this thing until unless we see that there is no change of labels across 2 subsequent iterations. Either we stop at that position or we stop when we see that the change is very minimum. So there is only 1 or 2 change, we stop there. Okay. This is asynchronous. Why this is asynchronous? It is asynchronous because here the updation process of nodes, so updation process of labels of nodes, this actually happens in an asynchronous manner, meaning that it is not the case that the updations of the labels of nodes are happening together. It basically happens one by one. I first look at node 1, then the updation of node 1 will affect node 2, the updation of node 2 will affect node 3 and so on and so forth. So this is happening in a chain like fashion. Whereas in the synchronous label propagation method, the updation happens together, meaning that the updation of node 1 will not affect node 2. The updation of node 2 will not affect node 3. These will happen independently. Okay? Meaning that the updation process will actually happen independently at every node, right? At all the nodes together. What does it mean? So let's again take the same example, same types of labels. Here labels are symbols, right? So let's take node 1. So say node 1 has this symbol and this symbol. Let's assume that we take this moon-like symbol randomly. So we will assume that, so we basically replace this heart by moon. At the same time, when this is happening, when node 1's label updation is happening, node 2's label updation is also happening. Okay. So when node 2, at the same time, when node 2 updates its label, node 2 looks at node 1's heart symbol. Node 1, it will not look at node 1's moon symbol, right? So node 2's decision will depend on node 1's initial label, node 5 initial label, node 3's initial label. Okay, and let's assume that, say we have heart, circle and plus, let's say the random choice is heart. Okay, let's look at node 3. Node 3 has these 2 nodes, right, two neighbors, this moon-like structure and this stop structure, and let's assume that the majority, the random symbol that we'll take is the stop symbol, and so on and so forth. So things are happening together, so that the output of one's update will not affect the output of other's update. So this is the updation after first iteration, right? So therefore this is called synchronous label propagation. Things are happening synchronously. Now after this we will have the next iteration in the same way, and we will keep on doing this thing until we'll see there is no further change. Okay. So these are methods. Now what's the problem here? The problem here is that this is kind of some sort of it basically follows a random process, right? Because it is not stable, because the iteration 1 in a particular sequence would be different from iteration 1 in another sequence. So, and you may end up having a different output altogether, right? It also depends on the seed node selection, by the way, right? It is random, because when we choose these labels from your neighbors randomly, right? So, in one iteration you choose say heart symbol randomly, in another iteration you may choose say plus symbol randomly. Okay, this randomness would make this thing would make the output also non-unique. Okay, it also has the stability problem. So, there are many other methods that generally we use for overlapping community detection. If you want to know about the holistic methods that people generally use for overlapping communities, this is the survey paper that you should definitely read. This is a very nice survey paper on overlapping community detection methods that people use for networks. Okay, if you want to know about disjoint community detection algorithms, you should look at these two survey papers. This one, both the survey papers are by Santo Fortunato, who is also one of the very prominent researchers in network science. You read this paper, community detection in graphs, community detection in networks, a user guide. These are very comprehensive survey papers. If you want to know, about the metrics, because community detection is all about metrics, right? It's basically a game of metrics. So, permanence, modularity, CART, conductance, all metrics, right? If you want to know more about the metrics, we wrote a survey paper on only the metrics used for community analysis. So, you may want to read this survey paper as well. Okay. So, let us now move to the next part, which is local community. Okay. So, if we remember at the beginning of this chapter, I mentioned that there are basically 4 types of community structures. One is called disjoint community, the other is called hierarchical, the overlapping community, third one is hierarchical community. These 3 community structures we have already discussed. The fourth one is local community, which basically says that, given a node, you detect the other nodes present in the same community where the given node belongs to. Okay. So, we explain one method which is called local modularity based method, right, and we will see that we again define another quantity, another metric, and based on that we detect local communities. Okay. So, here the idea is that the graph structure, the entire graph structure may not be known to us, which is also very obvious, right. So, when we scrape Twitter or when you scrape Facebook, although Facebook is not, you can't scrape Facebook because of the privacy issues, but let's assume that you scrape a website, right, and it may not be possible to scrape the entire website, say Twitter for example. You can get only 1% or even 0.1% of the Twitter network, right, and you are interested in knowing the community information of a single node. Okay, so you can use local modularity. What is local modularity? So, in the local modularity, you have an unknown portion of the graph, and you have the known portion of the graph, and you also have the unknown portion of the graph. Unknown portion is not known to you, and say you also do not know the connections in the unknown portion, but the known portion you know the complete connections. Okay. So, based on the known portion, you can create this adjacency matrix Aij. Now, this Aij is 1, right, if I and j are connected, and both of and either I belongs to the particular graph or particular portion which is known, or j belongs to the particular portion that is known. Okay. And what is the idea? The idea is that, say you have this known portion C, okay, let us say this is the community C, you all know the edges, right, but you do not know the other other edges which are not part of C. You gradually explode the network. You gradually explode the network based on this modularity, local modularity metric, and you keep updating it. This is the idea, right? So what is the, what does this local modularity look like? It is basically a fraction of this one. What is this function? This is basically again an indicator function, which basically says that if I and j both belong to the same community, then this is 1, otherwise 0. And what is the remaining part? So the denominator is basically all the edges. So it basically says that what is the number of edges inside the known community, known portion, and what are the total number of edges, meaning that within this community edges and community and the edges which are outside this community. Okay, this is local modularity. Now let us see how can you use local modularity for local community detection. Okay, so this is C. So C is something that is C is basically the community that you have already explored so far. So you start from a node and you are basically growing the community of that node, right? So at the beginning the node belongs to its own community. So at the beginning there is only one node in the community, and then you gradually keep taking the neighbors one by one into the community, and you grow the community. Okay, so this portion is the known portion. Okay, known portion meaning you basically know the edges within the community. Okay, within the known portion. Within the known portion, now we basically create two regions. One region is the C, and other region is the W. This is the W region, right? So W region corresponds to the peripheral part of the known community, and C is the central part of the known community. What do you mean by peripheral part? So peripheral part of the community basically consists of those nodes which have at least one edge which are pointing outside the known region, something like this. Okay, so these are basically the peripheral portion of the known part. What's the core portion? Core portion consists of those nodes which core portion consists of those edges which are completely internal to C. Okay, those nodes which do not have any attachment to any node outside C. Okay, and you have the unknown portion. This is the unknown portion that you do not know. You do not know anything about the unknown portion. You basically keep exploring, right? So at the beginning you have both. So you start from a particular node. This node forms both C and W initially. Okay, then what you do, you choose one of its neighbors one by one. Okay, you choose it and you basically pick it inside the community, and then you measure the local modularity. So how do you measure it? Let us define another adjacency matrix called boundary adjacency matrix. This is A cap. So A cap ij is either 1 or 0, right? So if A cap ij is 1, it means that both I and j are connected, and either of I and j are part of W. What does it mean? It means that it will basically have nodes, right? It will have nodes, and these nodes can be connected to C, right? Or can be connected to U. Either I or j belong to W. otherwise 0. Okay? And then you define this local modularity, which is the ratio of the denominator is that for all ij which are part of this known this known part, this known graph, a cap ij, a hat ij, right. So what does this mean? Summation of all you know a ij hat. It basically means the total number of edges with at least one endpoint in W. See here, I and j are connected and at least one endpoint is W, right. So it is basically considering all the edges which are pointing to either C or outside or U. So this edge, this edge, this edge, this edge. So those edges which are basically you know starting from nodes which are part of W, right. And what is this numerator? Numerator is out of all such edges, right, which we have considered in the denominator, we only take a fraction of that, right. We use this indicator function delta. What is delta ij? Delta ij is 1. Look at it carefully. Delta ij is 1 when I belongs to W and j belongs to C, or vice versa, meaning either endpoint belongs to W and the other endpoint belongs to C. So meaning I am basically looking at you know these edges, these kind of edges. One belongs to W and the other part belongs to C. This is the numerator, and the denominator, these kind of edges as well as these kind of edges. Okay, it kind of measures the fraction of edges which are coming from W. How many of them? I mean, out of all the edges which are coming from W, how many of them actually moving to C? You can think of it as a fraction of you know internal edges versus external edges. Okay, so we basically measure this local modularity value. We start from a particular vertex for which we want to detect the community. We add one neighbor, right, independently at random, and then we measure this quantity. If this is high, then you add it, otherwise do not. You keep on adding until unless you see this value increases, and then you stop when there is no further increase. This is a simple way. You can also make it complicated. You can say that okay, let us first grow the community and then again you refine it, because this is ultimately greedy, right. At the end of the day, it may happen that some nodes which have been added earlier should not have added, right, should not have been added. So you want to remove those nodes as a post processing steps, right. That can also be done. So this is local modularity. So local modularity is generally used for community searching. So let's try to understand these two terminologies. One is called community search, other is called community detection. Community search is basically given a node, you return the community where the node belongs to. You are not thinking about other communities. And what is community detection? Community detection is basically returning all the possible communities that are there in the network. One can say that you know if you know community detection algorithms, you can also do community search. Yes, if you know the community detection, if you know all the communities, then it is basically returning a community, particular community, right, given a query node. But why do we really need to detect communities when it comes to community search? Because community detection it is very expensive. You need to look at the whole network, right. So community search is basically easier than community detection, faster than community detection, and sometimes we do not need all the community structure, all the communities in the network. We need only one community or two communities, right. So that's the difference between community detection and community search. Okay, so we stop here. So in the next lecture, which is going to be the last lecture of this chapter, we will discuss how do we evaluate a community structure, right. We have already discussed metrics like modularity, permanence, right. Those metrics can be used for evaluation, but there are certain problems. We will discuss those problems in the next lecture, and we will see what are the ways we can evaluate community structure. Okay, thank you.